Hey everybody, Trey here. Welcome back to another video. Back with another case study for today, and we're going to take a look at one of the more unique events to occur in the last several years, and that was the Pilger, Nebraska twin EF-4 tornadoes on June 16th, 2014 that were part of kind of a localized tornado outbreak from a couple of supercells across central and northeast Nebraska on that day. Obviously a very rare sight for any chaser or storm spotter who was on this storm. It's not often you see two strong to violent tornadoes ongoing in such close proximity to one another. Usually, if you do have simultaneous tornadoes, one will be strong and one will be weak. Either the old tornadic circulation is occluding and weakening, and you have a new circulation taking over and dropping a tornado, or you have a very weak satellite tornado rotating around the main tornadic circulation that is usually much larger and stronger. That was not the case here. You had two EF-4 tornadoes within a few miles of each other from different mesocyclones, and each tornado was able to thrive for a period of time. Usually one starts to dominate very quickly if that's the case. Not the case with the Pilger setup. So we're going to, of course, go into the meteorology behind the event and at least try to answer why this may have happened. Of course, meteorology is filled with a lot of cases where things happen and we just don't know why, and I think this might fit into that. But we'll at least try to answer that and give you some of the meteorology behind the event that made this event so notable. As always, I like to give you guys some research articles on these events so you can do a deep dive yourself. Not much peer-reviewed literature on this event, but we do have the National Weather Service office in Omaha. They have their page on this event that goes over the tornado tracks for each tornado here with the Pilger storm, some photos, radar imagery, storm reports, and an overview of the environment. So if you're looking for a little bit deeper of a dive here on this event, I'll put this link in the description to their event page. So without further ado, let's go ahead and get started here. We'll give you some context to start things off here. This was the Day 1 Storm Prediction Center outlook on the morning of June 16, 2014. We had a moderate risk out for extreme southeast South Dakota, eastern Nebraska, into much of the northern half of Iowa. 10% hash tornado probabilities in that same corridor, with the threat for strong tornadoes identified there, as well as a damaging wind and significant large hail contour there, focusing on that 45 hash contour there for large hail in northeast Nebraska into northwest Iowa. So the potential for tornadic supercells with pretty much all hazards were there in this event, but there were some interesting kind of caveats to this event that kind of made things uncertain early on. And by 20Z, those things kind of cleared up, and the tornado probabilities were bumped up to a 15 hatch right there, focusing on northeast Nebraska. So the threat for strong tornadoes became a little bit greater as the day went on, hence the upgrade. So we'll start off with some radar data here. We had an early batch of storms to deal with on the morning of June 16th. You can see as we go forward in time here, you can see a couple separate areas of storms fire up there across southern South Dakota into central and eastern Nebraska. As the morning went on, you can see that kind of separate area. The northern area kind of bowed out there in eastern South Dakota. Separate area of storms there near the Nebraska-Iowa border. And these were the result of warm air advection, or WAA as we call it colloquially. And all that is the transport of warm, moist air into a region, usually the result of a surface low out in the kind of western plains, really helping to strengthen and back the flow in the low levels to really pump that moisture northward. And if that low level warm moist flow is able to interact with a frontal zone, usually it rides up and over a frontal zone, that can provide enough lift for storms, usually elevated, to fire. And you'll often see this in the overnight hours of an event or in the morning hours of a given severe weather event. You'll get these warm air advection storms. And if we look at our surface map, this is for 15Z, so 10 a.m. Central Daylight Time here. A couple things we notice right off the bat. You can see a surface low down here across kind of northeast Colorado, and a secondary surface low up here, kind of the Wyoming-Montana confluence area there. You can kind of see that kind of broad cyclonic flow there at the surface. And from this northernmost low here, we had a warm front extending down to the south across southwest South Dakota into central and southeast Nebraska. So a little bit difficult to kind of really pinpoint where this warm front was, but it's going to be kind of somewhere in this vicinity right here. You can see the wind shift across it. southerly or south-southeasterly winds to the south of the boundary, and to the north of the boundary we had easterly or east-southeasterly winds. So definitely a wind shift along that boundary. And as that warm, moist flow rode up and over that boundary, we were able to get storms to fire there across central Nebraska into southern South Dakota. Most of them started off as elevated. A few would become surface-based as they moved off to the east throughout the morning and early afternoon hours, producing some severe weather reports here across Iowa. But these early storms did pose some questions on the degree of air mass recovery in eastern Nebraska behind the initial wave, as well as if any boundaries, outflow boundaries in particular, would emanate from these clusters. And as far as that initial point there, as far as air mass recovery, that wasn't too much of an issue here. So here's our visible satellite. You can see that early band of storms there across eastern Nebraska, moving off toward the east as the morning progressed. You can see some clouds behind it, but by the early afternoon hours, those really started to break up and become a lot more cumuliform in nature. You can see kind of the bubbly cumulus there with plenty of breaks in the clouds. So surface heating was not really an issue with behind this early wave of storms. And we'll talk about the surface pattern and any boundaries here in a second. But that early batch of storms was able to move off toward the east pretty quickly and leave a nice batch of kind of broken skies there in its wake, perfect for heating up the surface and allowing that instability to build. Let's now go to our synoptic pattern here. So we'll start at 500 millibars. And right off the bat, this is at 12Z on June 16th, so morning hours, June 16th. Fairly zonal pattern here across much of the United States here, kind of mostly just kind of broad southwesterly to westerly flow across at least the northern and western kind of portions of the country here. We had a nice trough digging down here across the Pacific Northwest with a kind of a secondary area here across southern into eastern Canada. So as the day began, we were kind of in this lull in between these two, kind of under this little ridge between the two upper-level troughs here. And so forcing was a concern to start off with. And we've talked about this in some previous case studies here. Keep an eye on these height contours here as we go through with time. Notice the location. And as we've said before, we want to see heights fall in a different region. So basically, if we're looking at a particular region right here at the star, and we have, let's say, our 5760 contour here, our 5820 contour here in the morning, on the afternoon of a severe weather event, we want to see those heights fall as we go through the day. So we want to see those contours advance kind of off toward the east, so we get heights to fall at our certain region. So we would want to see something like this, 5760, 5820. So at this location, heights have fallen throughout the day. Now, if heights rise throughout the day or are neutral, that means the overall forcing is not going to be super strong. It'll be fairly nebulous. With height falls, you get a resultant sort of rising motion, and with height rises, you get generally large-scale sinking motion, which is unfavorable for storm initiation. So keep an eye on those height contours here across eastern Nebraska as we go through with time. You'll notice that they don't really do a whole lot throughout the day. They kind of just sit there. And so heights were very much neutral across this region. So that was pointed out in the early SPC outlook that the forcing for ascent might be fairly nebulous given the lack of large-scale forcing for ascent. But I want you to notice here this little kink in the flow approaching central Nebraska into northern Kansas by early afternoon. There was just enough of a little shortwave here to just suppress that ridge enough and just allow heights to fall enough to get very isolated storm development. You can even see it better here at 21Z. Just a very subtle shortwave out ahead of this main Pacific Northwest closed low here. A little shortwave ejecting into the central to northern plains here was looking like just enough to get a couple of storms going. So we've talked about storm mode before. Of course, you have your orientation to the initiating boundary, and you also have forcing. The degree, I can't spell forcing. The degree of forcing for ascent plays a role in storm mode a lot of times. And if you have very subtle forcing, that may only allow a couple of discrete storms to fire, and therefore you're at less risk of allowing storms to form into a line quickly and reducing the overall tornado threat, becoming more of a damaging wind threat. Instead, in these subtle forcing scenarios, often you'll get just a couple of storms to fire, and that was the concern here with this setup, given such subtle forcing here in the mid and upper levels. We'll go down to 700 millibars, see if we can kind of better see this little shortwave here. And you'll see as we go through with time, you can definitely see it right there. Kind of the frontal zone. This looks to be maybe some of the some semblance of the frontal zone aloft here. So definitely a little bit of a kind of shortwave here in the flow there across northeast Nebraska. Some trailing shortwaves back in here. And so I think you can a little bit better see it at 500 millibars. Here's at 21Z though. You can definitely see a little shortwave in the flow there. Even more pronounced off toward the north. So very subtle, sort of shortwave out ahead of the main wave here at 700 millibars, matching what we saw at 500 millibars. We'll go down to 850 millibars as well. Take a look at our low-level jet. You can see in the morning hours we had already a very broad air mass that was warm and moist here across much of the southern plains to the northern plains here. Already 40 plus knots of flow here at 850 millibars, helping to really pump that moisture from the south up into the region. As we went on through the day, that gradient would tighten there. You can see some semblance of the dry line here at 850 millibars there. Nice dry line bulge there into Kansas. And a very strong low-level jet here, 40 plus knots here across the eastern half of Nebraska as we went on into the early afternoon hours as storms started to initiate. Let's go down to the surface here, and we'll start out with our data. So I'm going to start here at 18Z, just because that is kind of well after those initial storms had moved off toward the east, so we were already starting to see recovery back here. So you'll notice 70s dew points here across much of the region, Kansas into Nebraska. So very warm, moist air here at the surface, temperatures into the mid to upper 80s here. But I want you to notice what we have going on here in northeast Nebraska. Very much a temperature and wind shift kind of gradient here across the region. And actually, let me kind of draw it back in here. So this is at 18Z. Notice here, we have an outflow boundary extending from southeast South Dakota into central and eastern Nebraska. And this was from our early convection. And this would lift northward with time very slowly throughout the day. And of course, we know what happens with outflow boundaries. They provide, number one, an area of enhanced lift for storms to fire. And we already had a subtle enough forcing regime on the synoptic scale. This would almost sort of ensure that a couple of storms would fire here along this boundary due to the just slight enhancement of lift from this outflow boundary. You can see the convergence along it, winds on the north side of the boundary out of the kind of southeast, southerly winds to the south. So definitely a wind shift along it, which would allow for enough convergence to get isolated storms to fire along it. And also, as we know, it enhances the low-level shear along that outflow boundary. As we go through with time here, notice what happens with the outflow boundary. I'm going to put it in here, put it back in here, and then we'll go forward in time. So this is at 19Z, this is at 20Z, and I'll draw it in blue here where the outflow boundary is. You can see it has retreated north somewhat. We have 83 degree temperature here, 77 here at this observation, 78 up here, 88 out here, 84 here, 80 here. So definitely the outflow boundary had retreated toward the north just a little bit by 20Z, and by this time the combination of that shortwave moving in from the west and this outflow boundary was just enough to get an isolated storm to develop right along here, along that wind shift boundary that was kind of becoming a little bit more diffuse with time. And that is one thing I've noticed with outflow boundary cases. You really don't want a very sharp outflow boundary where you have, say, northeasterly winds on the north side of the boundary and kind of, southerly winds on the south side of the boundary. That provides almost too much forcing. This was just subtle enough of a wind shift here. You can just see by drawing the boundary here that winds were just convergent enough to provide another subtle forcing mechanism for storms to fire there. So this outflow boundary definitely helped things out and allowed the initial storm that would become the Pilger tornado producer to initiate. If we go toward 21Z, you can see it has retreated north even a little bit more here. Would probably put it somewhere right in here, right in there. So you can see it's retreated north just a little bit, and it was moving just slowly north, kind of lifting with the storm as it moved off toward the northeast. So it was keeping it in that enhanced zone of low-level shear for quite a bit of time, and that was definitely a player in the overall tornado potential with this storm. So just to kind of give you a broad scale view here of the surface, I'll just go toward kind of 19Z here. Broad surface low out here across the western kind of high western plains there. Of course, we saw kind of two different centers there in that morning surface map, but this analysis showing just kind of a broad surface cyclone there. Of course, backed and strengthening flow there in the warm sector of that surface low, with kind of that warm frontal zone there draped across eastern Nebraska out into Iowa there, with, of course, our outflow boundary, if we were to zoom in a little bit farther there, across northeast Nebraska. So this was definitely an environment that favored enhanced deep layer shear. Of course, we have, very strong southerly flow here in the low levels, with just kind of that broad, subtle southwesterly flow in the mid and upper levels. And that is kind of a setup that really piques my interest when I'm looking at severe weather setups. That just kind of broad southwesterly flow with a very subtle shortwave aloft to keep the forcing at a minimum and really only allow a couple of storms to fire. When you have deep layer shear and ample instability, which is what we had here, and we'll look at some soundings in a second, that is an environment that will oftentimes favor tornadic supercells later on in the day. So let's look at some soundings now. This is the 12Z Omaha sounding, so 7 a.m. at Omaha, Nebraska. A couple things we can see right off the bat. The moist layer, not very deep at all. The last few cases we've been looking at, the Joplin case, the May 3rd 99 case, had very deep moist layers extending up, usually past about 850 millibars. That was not the case here. Very shallow moisture. You can see that moist layer does not extend very far above the surface at all before we had a nice intrusion of dry air. And this was likely the result of the elevated mix layer. Of course, we talk about the elevated mix layer nearly every time in one of these videos, but the EML is that layer of warm, dry air that initiates near the surface in the kind of desert southwest to the higher terrain out west, and gets transported out across the plains above that kind of moist layer. And that helps, number one, cap the atmosphere so that storms do not fire early on and ruin the environment for later on. And they allow instability to build and build and build until that cap breaks, and then you can get explosive storm development once that elevated mix layer does erode. And that was the case here. Very strong layer, very deep layer of steep lapse rates here aloft along that elevated mix layer. So that was it was going to help cap the atmosphere through much of the morning. Of course, behind the initial activity that was able to remain somewhat elevated above this cap north of that warm front. And that was going to allow those storms to remain elevated for quite some time. But behind it, this capping inversion, thanks to the EML, would help suppress storm development in the warm sector behind that initial wave. And as you can see, we didn't really get anything behind that initial wave here. This was, of course, you can see the initial storms here move off into Iowa. Nothing here behind it. Just some nice cumuliform clouds there with lots of breaks in the clouds. No storms at all behind that. So that was concerning, given we had that kind of outflow boundary in place and the subtle forcing moving in from the west. So by 19Z here, we got another sounding, and this was of pretty substantial concern here. So let's go back to 12Z, and we can note the changes here. So this is the Omaha sounding at 12Z. Let's go to 19Z here, and you can see a lot has changed. We are up to now over 4,000 joules per kilogram of mixed layer CAPE. You can see just absolutely massive instability here in this profile here at Omaha. The elevated mixed layer was still in place, but we had substantial surface heating and warming. You can see the temperature up to 82 degrees. It was only 65 at Omaha through in that 12Z sounding. The moist layer had deepened quite a bit. So we had an increase in both surface moisture. You can see the dew point up there from 64 at 12Z to 75 here at 19Z. So very strong low-level moisture moving into the region. And the moist layer much, much deeper. We'd had some cooling and lifting of that capping inversion thanks to that very subtle shortwave moving in and that heating of the atmosphere helped lift and cool that shortwave, or that capping inversion. And by 19 to 20Z, we were completely uncapped here. A little bit of capping, mixed layer capping left, but very much that would erode in the next couple of hours. But let's note the hodograph here. This is an absolute unit of a hodograph if we're talking about, top tier tornadic supercell hodographs. A little bit of crosswise vorticity here in the surface. Of course, we talk about crosswise and streamwise vorticity when you have your storm relative wind vector and your horizontal vorticity vector, which is perpendicular to the hodograph. When those are more perpendicular to each other, that's when we have crosswise vorticity. And that is not as favorable as streamwise vorticity, which we do have that in spades here as we go up in the atmosphere just above that little near surface layer here. Notice here just about a half kilometer up, though we have lots of streamwise vorticity here. And so this was a very concerning look, and this was what helped prompt that upgrade to moderate risk with a 15 hatched there for northeast Nebraska. Just incredible instability with this kind of shear profile, especially the low-level shear profile, effective SRH above 500 meters squared per second squared, likely enhanced right along that outflow boundary. This was a recipe, given the discrete storm mode as well, for tornadic supercells, starting perhaps in the couple hours after this sounding was released. And let's go to some RAP soundings. So these are some RAP model soundings. This is at Norfolk, Nebraska, and this is where the storm kind of first fired and the first tornado was produced near the Norfolk-Stanton, Nebraska area. So this was in very close proximity to our eventual tornadic supercell. This is at 12Z at Norfolk. You can see kind of the same thing as we saw on the 12Z Omaha sounding. Lots of capping inversion to deal with here. Very shallow moist layer, 66 over 62, doesn't extend that far above the surface as well. So kind of jives with what we were seeing on the 12Z soundings. We'll skip ahead to 16Z. This was enough behind the early wave that the atmosphere was starting to recover. You can see that the moist layer has deepened somewhat, just above 850 millibars there. The low-level moisture was increasing a bit. Still had that capping inversion to deal with, strong elevated mixed layer there. But notice the change in the wind profile between 12Z, which was a kind of a long hodograph, limited low-level curvature there. And then we go to 16Z, and we've had a substantial increase in low-level shear. 0 to 1 kilometer storm relative helicity, almost 400 meters squared per second squared. So we'd had a significant change in the kinematic profile here in just a few hours' time. The low-level jet had ramped up to 30 to 40 knots here out across eastern Nebraska. You can, if we recall our 850 millibar map from the morning, eastern Nebraska was in a little bit of just a little bit removed from the overall strongest portion of the low-level jet here. You can see out here we were a little bit on the weak side, just east of the low-level jet axis there, 40 to 50 knots here out in kind of west central Nebraska. But of course, throughout the day, as that surface low, that low-level cyclone took place, and we got that low-level jet to kind of enhance and move off toward the east, and that helped really beef up those profiles there at in the eastern portion of Nebraska. So this was a rapidly improving environment here. This is at 18Z, still that capping inversion in place. And between 18 and 20Z, that's when we had that full erosion of the cap there. We go from 18Z, where we had that capping inversion really strong right there, to this at 20Z. And you can see what happens. The moist layer is just incredible here, up to about 700 millibars. So a very substantial increase in the depth of the moist layer, as well as the moisture at the surface. Dew points up to 73 here at Norfolk by 20Z. In this kind of profile, substantial instability, almost 4,500 joules per kilogram of mixed layer CAPE there. With this kind of profile, you can see that that little crosswise component had really worked itself out here near the surface. So we had ample streamwise vorticity in almost the entirety of this hodograph. You can see here as we go up, even somewhere like 3 kilometers up here, notice how much streamwise vorticity there is to play with. Here's our horizontal vorticity vector. And this was a very concerning look. Ample streamwise vorticity, very strong low-level shear, over 400 meters squared per second squared of effective inflow layer SRH. Any right-moving supercell in this environment was going to produce some pretty big issues given such large instability and such large low-level shear and streamwise vorticity. By 21Z, this is at Sioux City, a little bit off toward the east, as the storm was moving off toward the east of the Norfolk-Stanton area. By this point, it was moving toward Pilger. You can see much of the same. Lots of streamwise vorticity there in the low levels. Very strong instability, including low-level instability here, 0 to 3 kilometer cape of 134. So this streamwise vorticity was really going to be tilted and stretched into the vertical very efficiently, and that's why we had such a cyclic tornado producer form here. So let's take a look at some radar data here. This is just before 3 p.m. Central Daylight Time. Our storms first fired up here, kind of along that outflow boundary in northeast Nebraska. You can see kind of just a bunch of different showers here early on, but didn't take long for these storms to beef up. In just a few minutes' time here, we got kind of 3 separate kind of storms here. You can see this one here, the middle one, and the northern one. And we've talked about this before. In strongly sheared environments, sometimes it takes a clustering of updrafts like this to kind of produce a kind of larger dominant updraft / supercell that is fully able to take advantage of the strongly sheared environment. And that was kind of the case here. You kind of had these 3 kind of updrafts working together, and eventually we got the southernmost storm to kind of dominate here, and this would produce the first significant tornado of this supercell's life cycle near the Stanton, Nebraska area. You can see kind of that southernmost supercell kind of dominating here, hook echo here. A little bit of that remnant kind of northern storm off to the north there, but we kind of have now a dominant larger supercell able to fully take advantage of this kind of extreme environment. And this was some footage of the first Stanton tornado, the first tornado of this supercell. You can see right away it was a pretty beefy tornado, and this would produce EF-4 damage as it moved off toward the northeast. So very strong tornado there. And as the storm moved off toward the northeast, it would become quite a bit more interesting. Note here how this storm is all by its lonesome. Nothing around it here at all. Just this kind of storm all by itself. Very, very discrete. And that is the product of such subtle forcing. You have that subtle shortwave aloft with that outflow boundary. Those combine to produce just enough forcing to initiate just this one kind of storm, one area of storms here along that outflow boundary in northeast Nebraska. So again, as we move on in time, goes off toward the north, this storm continues and was a cyclic tornado producer. In this kind of environment, these are going to be cyclic tornado producers. Given very strong instability, very strong streamwise vorticity, these storms were going to produce tornadoes as long as the inflow remained unimpeded. These storms remained by themselves, and that was going to be for quite a while until it moved into the stable air up in far northeast Nebraska into South Dakota. So we move on with time here. The storm continues. Some showers start to form to the south and kind of evolve into, emerge into this ongoing supercell. And let me go ahead and zoom in here on this storm. So this was the storm as the initial Stanton tornado was weakening and the Pilger tornadoes were forming. So the initial tornado weakening, and then we get kind of these showers here flowing up into the forward flank region of the supercell. Now you can see 2 different areas of debris ball there, and this was as we had the Pilger twins ongoing. And this was a very interesting evolution here of these 2 tornadoes. We kind of get one big sort of debris ball here as the tornadoes moved close to each other, and then the storm continued to move off toward the northeast. Let's look at it here in velocity. So very interesting progression here with these tornadoes. And we're going to talk about what this is actually called here in a second. But notice here, this is the original Wakefield. This is the original Stanton tornado here, occluding off toward the northeast. This is just before 4 p.m. We get our first Pilger tornado to develop as the Stanton tornado was moving off toward the north and weakening. So our first Pilger tornado right here. And then quickly we get a second tornado to develop. Here's our first one, here's our second one. Both strong couplets, both in very close proximity to each other. But notice what happens here. They kind of rotate around each other. You can see that initial, that easternmost one originally kind of goes to the north and then comes and loops around, so that this was the second tornado here. This is our first one. So they kind of rotate about each other, and that is called the Fujiwara effect. You may have heard that before with tropical cyclones, and it's a little bit easier to see on this this graphic right here. This is from U.S. tornadoes here, and the thick lines are going to be the tornado tracks. So there's the purple line there. That is our Stanton tornado, our initial tornado from this supercell. Moved off toward the north. We got our first Pilger tornado to occur there to the east of Stanton. The second of the Pilger twins formed there just to the south of Pilger. And watch the tracks here as they go forward in time. You can see they kind of wrap around each other and kind of do a loop around each other up here to the northeast of Pilger. That is called the Fujiwara effect. And this is what happens when you have two vortices in close proximity to each other that are rotating the same way. So if you have one here and one here, they're going to rotate about their common center. These both have kind of a pull on each other, and so they're going to rotate about a common center, and oftentimes they will undergo what we call a binary interaction and kind of form into a larger sort of single vortex. You see this in tropical cyclones quite a bit, but it can also happen rarely in tornadic events. You can see here we have two vortices rotating the same direction here, two tornadoes, two cyclonic tornadoes, and they kind of pull on each other. So they're going to rotate about their common center, kind of in the middle of the two. And you can see that clearly here in the radar imagery. The easternmost one was kind of pulled in, kind of rotated about the common center there, and eventually we got the tornado to dissipate, and then we had our last tornado of the supercell near the Wakefield area that was also an EF-4. One thing here, we can look at the correlation coefficient just to see how big and how notable this was on radar as far as tornado debris. This was our initial Stanton tornado debris signature, our initial Pilger tornado debris signature. You can see quickly there, two different debris signatures here in close proximity to each other. Very clear evidence of two tornadoes in progress at once. Then we kind of get one sort of big area of debris as the Fujiwara of these two vortices occurred, and ample debris was lofted from both these tornadoes, and they were in such close proximity to one another that they just kind of showed up as one big debris signature on radar. So here's some footage here of the initial Pilger tornado, and then the second tornado that developed just off to the east of the initial circulation. See the camera pans off toward the east here, and just another area of massive circulation here. This was the second tornado, and again, this is such a rare situation to occur that you have two separate mesocyclones and two separate violent tornadoes ongoing at the same time in such close proximity. That just doesn't happen. One quick thing about these tornadoes. This is some of the most insane footage I've ever seen. Just incredible footage here of these tornadoes. Notice the horizontal vortex here, rotating just aloft, just above the surface there. That is usually reserved for stronger tornadoes. We saw that in the Tuscaloosa tornado, the Henryville, Indiana tornado. We've seen that very often, and these are usually reserved for very strong tornadoes. Just an evidence of how much streamwise vorticity there was in the environment, and that oftentimes results in these sort of horizontal vortices orbiting around the parent tornado. Let me just kind of go forward here, show you just absolutely incredible footage. You can see the first one here and the second one forming out behind this initial tornado as it moved near Pilger. So very, very interesting, unique event. And kind of just to finish off here, this radar overview. So you can see two separate debris signatures there as we got two different tornadoes right there. And then we got kind of that initial one to occlude, and then we had our last tornado of the event near Wakefield that produced an EF-4 as well. So this is some footage from Skip Talbot. This was one of the remaining Pilger tornadoes, and this was the Wakefield circulation here. Notice how fast this moves. This original Pilger tornado moves here as we play the footage. Notice how much it accelerates here. As the RFD swings around this bigger Wakefield tornado, it really surges and pushes this tornado. And look how fast this tornado is moving. It is moving incredibly, incredibly fast around in close proximity to that new Wakefield tornado. They calculated this to be moving at about 95 miles per hour. That is, I believe, the fastest tornado on record, and just goes to show you how dynamic this event really was. Let's watch this again. It's kind of mesmerizing here. Again, as the RFD pushes around, you can see the clear slot up in here. As that RFD pushes around that Wakefield tornado, it really surges that original Pilger tornado forward. Just look how fast it's moving. That's just incredible to watch. And so that was our Wakefield tornado, our final tornado of the from this particular supercell, and it was a beast nonetheless. Now, there's an oft-forgotten storm from this outbreak that occurred back off to the west later on in the event. So we'll go back to our broad view radar imagery here. Here's our Pilger storm near that outflow boundary, moving off toward the northeast. And then we got initial renewed development out here back closer to the dry line out here across central Nebraska. And this storm actually produced a tornado as well near the town of Burwell. You can see that here. Beautiful cone tornado here near the town of Burwell. Very photogenic tornado. But this tornado is often forgotten because of how prolific the Pilger tornadic supercell was. So let's go back to our surface data here. So this is at 22Z, 5 p.m. Central Daylight Time. And so we were well removed from the outflow boundary out here across northeast Nebraska. So we had to kind of rely on the dry line and the overall kinematics of the event back out here to the west to initiate storms. So here you can see our dry line. Pretty clear where that dry line is located. 40s and 50s dew points out here to the west of the boundary, 60s and 70s out here to the east. So our dry line's somewhere in there across kind of west central Nebraska. Again, you can see that outflow boundary is kind of washed out here across northeast Nebraska. Winds mostly just out of the south here across the region, so that outflow boundary had become much more diffuse across the region. So our dry line was back out here. Of course, we had that little shortwave that was kind of moving into the region, kind of right over the region as we speak. And that was just enough to get a storm to fire out here along that dry line. If we look, let's look at our environment out here to the west. This is the 22Z RAP proximity sounding from Ord, Nebraska, which is very close to Burwell. This is at 22Z. You can see we are, once again, in an environment of very high instability, over 4,500 joules per kilogram of mixed layer CAPE, over 150 joules per kilogram of 0 to 3 kilometer CAPE. Deep moist layer here at the surface, extending up about 800 millibars here. So 84 over 70, so very juicy air here just east of that dry line, and a completely uncapped atmosphere. But notice that the wind profile is not as favorable out here to the west as they were out toward the eastern portion of Nebraska. We did have a little bit of curvature here in the low levels for any supercell to take advantage of. Photographs, although not quite as long here. You can see bulk shear, only about 36 knots here at Ord at 22Z. So the overall deep layer shear, we were just kind of removed from the main sort of portion of that shortwave here. Just enough to kind of weaken the shear a little bit in a deep layer sense. As we went to 23Z, we continue to get that moistening here in the low levels. You can see that moist layer up above 700 millibars now, so extremely deep moisture out toward the east of that dry line. Still very strong instability, and a modest increase in low-level curvature here. You can see the veering winds in the low levels. About 200 meters squared per second squared of effective inflow layer, storm relative felicity here. So any supercell that was able to fire along that dry line would be able to take advantage of an environment favorable for tornadoes. Maybe not strong tornadoes or cyclic tornadic supercells, as was favorable more east of this area. But we were seeing enough of evidence to favor isolated storm development that would potentially produce tornadoes, as well as large hail out here. You can see a bunch of different significant hail analogs here. Very strong instability in that kind of mid-levels there, and a much weaker low-level shear out here than it is to the east. Of course, we've talked about this before as well. Some new research from people like Cameron Nixon who have shown that strong low-level shear, as we saw out to the east, is not nearly as favorable for large hail as it is in more weakly sheared environments in the low levels, and this kind of fit the bill there. Still adequate low-level shear for tornadoes, but much weaker than it was out to the east, and therefore the hail threat was a little bit greater out with any supercell that fired out here along the dry line to the east. So let's look here at our reflectivity here. You can see this is at 4:30 p.m. We got our first blip here out in kind of west central Nebraska. Would quickly move off toward the northeast and intensify in a very unstable environment there. Quickly became a supercell here. You can see it undergo a bunch of different mergers there, and finally we get a nice supercell to develop. Hook echo develops there just after 6 p.m. Pretty much a classic supercell here. And this one, once again, very subtle forcing. You can actually see the dry line out here, out to the west. Maybe we may have had a little bit of influence from the remnant outflow boundary extending out here to the west, but again, it had become much more diffuse out here. So we were, again, relying on the dry line to initiate the storms and the overall environment to that was a little bit more marginal than it was out to the east to produce the hazards associated with this supercell. But moved off toward the east pretty quickly and produced a couple of tornadoes out here, including that one near Burwell. We move on to our velocity imagery here, and you can see it quickly kind of becomes a supercell there and becomes tornadic as it moves off toward Burwell, which is right in here. Again, a very photogenic tornado out there. And yeah, that was the second kind of little sister to the Pilger storm out here in this event. And then eventually, as we move on with time, this activity started to sort of merge with the initial kind of warm air advection activity out toward the east, and would become a much more clustered linear sort of mode as we went on into the evening and overnight hours on June 16th and 17th. So the question here is, why twins? Why were two significant tornadoes able to coexist for a decent period of time rather than one kind of killing off the other? And again, meteorology is full of these events where things happen and we don't really know why. And I'm kind of leaning that way with this event. A couple of thoughts here I have is, number one, that I've always said that when you have extreme instability like we did for this event, the rules kind of go out the window. And we've seen this in the past. For example, the Gerald, Texas event from May 27, 1997. Sneak peek at a case study that's coming up in the coming weeks. But that event had 6,000 to 7,000 joules per kilogram of CAPE with very little ambient wind shear. The wind shear was somewhere near 15 knots. The upper level flow was about 15 knots. So very much not a significant tornado environment. But you had 6,000 to 7,000 joules per kilogram of CAPE. You had a boundary in play, and you got an EF-5, a very destructive EF-5 tornado out of that. El Reno, 2013, May 31st, 2013, the infamous El Reno tornado that unfortunately took the lives of Tim Samaras and his crew. That one, very large instability as well, 3 to 4,000 plus joules per kilogram of CAPE. You had a stationary front / boundary kind of in play. And when that happens, when you have very strong instability with kind of that boundary, that low-level shear enhanced along the boundary, some strange things can happen. Of course, in the El Reno case, we got the largest tornado ever recorded, 2.6 mile wide tornado with 300 mile an hour winds. And then here in our Pilger event, very strong instability, 4,000 to 5,000 joules per kilogram of mixed layer CAPE along an outflow boundary in an already primed kinematic environment for cyclic tornadic supercells. You add the enhancement of the low-level shear along that boundary in such an unstable and extremely unstable environment, that's going to do some weird things. And that likely played a factor in the fact that we were able to get two significant tornadoes side by side. Likely, I think what happened was that you had this so much streamwise vorticity along your outflow boundary that the supercell was just able to, a new area of mesocyclone formed in proximity, and usually they're going to fight for the inflow, but there was just so much streamwise vorticity that you got a significant tornado out of it in such an unstable environment. Here's a schematic diagram from Lemon and Doswell, 1979. I will put that link to that paper in the description. It talks about tornadogenesis processes. But this is kind of our schematic diagram here. Here's our kind of what it looks like on radar. Hook echo, flying eagle shape, forward flank here. Here's our rear flank downdraft spreading out on the southwest flank of the storm, and that along that rear flank gust front, in where that interface is between that and the inflow to the storm, is where you get your tornadoes. And you probably got two different areas of rotation, and given such strong low level and deep layer instability and such strong low and deep layer shear and streamwise vorticity, we were just able to get two different tornadoes to coexist and become strong and thrive for a period of time side by side. So, there's not really a definitive answer as to why this happened. But once again, I always say when there's extreme instability and strong shear, the rules kind of go out the window, especially when you have an outflow boundary or some sort of boundary in play. So that's going to do it for this video. Hopefully you learned something about this event. Again, such a unique event, one that is really, really interesting to study. So thanks for watching. We'll see you in the next video.